Let's take a look at an application of finding a particular solution when we're looking at position, velocity, and acceleration. So if we remember, those three things are related to each other with the idea of derivatives, right? That the derivative of position is velocity, the derivative of velocity is acceleration. So if we have this derivative chain and now we're thinking anti-derivatives, we could now work in both a forward and a backwards direction. So let's take a look at this example. A ball is thrown upwards with an initial velocity of 64 feet per second. So I throw this ball up in the air, and I throw this at a height of 80 feet up in the air. Using the fact that acceleration, and the only acceleration is due to gravity in this case, is going to be negative 32 feet per second squared, we're going to find both of the velocity function and a position function with respect to time. So if we think about this ball, and if we throw the ball up in the air at 64 feet per second and you're 80 feet above ground, that ball is going to have a position to it, right? It's going to go up. It's going to start at 80 feet. It's going to go up, I don't know how far, and then it's going to go back down. We'd like to figure out what that function is. Also, same thing with velocity. It starts out at 64 feet per second when you throw it up, but when you throw something up, it starts to slow down, right? It doesn't speed up in the air, right? It slows down. Eventually, it's going to stop, and then it's going to start to speed up as it falls to the ground. So we would like to find both of those functions and see how do they relate to all of this given information. So if we think about the relationship that I said of acceleration, position, and velocity, we don't know the position. We know the initial position, but we don't know the position function. And I don't know the velocity function, but I do know the acceleration function. So I know my acceleration. The acceleration function is going to be negative 32. At any given time, the only acceleration is a constant negative 32. So to be able to go backwards now, to be able to figure out what is the velocity, well, I need to take the integral of this. I need to anti-differentiate and work backwards. So we have that the integral of acceleration is going to be equal to velocity. So the velocity is going to be the integral of acceleration, and I'm going to do this where t is the variable. So my velocity is going to be the integral of negative 32 dt. So if I take the integral of a constant, I just get a constant times the variable plus c. So this becomes negative 32t plus a constant. So my velocity function that I have, v of t, is equal to negative 32t plus c. So this is true, right? That this is the antiderivative, but I have this piece of information that my initial velocity is 64 feet per second. So if we think about initial, we have to figure out what does that mean for t. Well, if we think about starting something, we usually start at time 0. So we know that v of 0 is equal to 64. So this is that initial condition. This is the little piece of added information about my function that will allow me to solve for this constant t. So if I plug in t equals 0 here, I have v of 0 is equal to negative 32 times 0 plus 64. Now, oops, sorry. That's the answer. Sorry. So we have plus c. Now, this we know must be equal to 64, right? Or you could put 64 on the other side if you'd like, whatever. But all I know is that v of 0 is equal to c. But that also must equal 64, so that says that c is equal to 64. So my velocity function is negative 32t plus 64. So this is my unique velocity function that will give me the velocity of the ball as it's being thrown up in the air and then as it's starting to go down. Okay, now we found the velocity, now we'd like to find the position. And so seeing the same property that we saw over here with taking the integral of acceleration, we get velocity, we can do the same thing with velocity and position. I can take the integral of velocity to find the position, so I'm going to do that. So my position, we always just use an s of t, that just happened to be the position function. S of t is going to be the integral of v of t dt. So with t being my variable, I can take the integral of velocity to get position. So my position is going to be the integral of negative 32t plus 64 dt. So here I add 1 to the power of t, so I have t squared. I divide that by 2. I know negative 32 divided by 2 is going to be negative 16, so I'm going to have negative 16t squared. So add 1 to the power to get 2, divide by 2, I get this. Do the same thing here now. I add 1 to the power of t, so I have just a t to the first, divided by 1, I get this. But now I also have plus a constant again. So this is my position function is given by this. But again, just like how with this initial information we had about velocity, I could also use that we had this initial height of 80 feet. So what we know that s of 0 is equal to 80. So I can plug that in. So I know s of 0, if I plug in t equals 0 everywhere, I'm going to get a negative 16 times 0 squared plus 64 times 0 plus c. All of these zeros become 0, so I have that's equal to c. But I know then that if this is equal to 80, that these two must be equal, so I see that c is equal to 80. So my position function is given by negative 16t squared plus 64t plus 80. Now, in general, we could create formulas for anything based off of this. So instead of using our specific a of t was equal to negative 32, if I just start out with a general constant being acceleration, so let's say, for instance, I'm going to call a of t is equal to a. I could now find the velocity based off of this. So the velocity is going to be the integral of a of t dt, so that's the integral of a dt. So that's going to be at plus some sort of constant, v of t. Right, so I'm going to generalize this process. So for those of you who want to be engineers and want to do physics with calculus, this is what you're going to be looking at, is seeing how do we generalize this to anything using integrals. So my velocity function is always going to be this. So we're saying this is going to be my acceleration. Now this plus a constant, as we saw, that's going to, if I plug in 0, that same number that appeared there is going to appear as my constant. So if we know, say, if v of 0 is equal to the, let's say v sub 0, which is going to be my initial velocity, this goes to 0, this is equal to v sub 0, so c is going to be equal to v sub 0. I'm going to get v of t is equal to at plus the initial velocity. So you may have seen this function in physics in high school, that you might have said, okay, this velocity at any given time is the acceleration times time plus my initial velocity. We can go one step further, just like we did before. We can now take the integral of this. So my position function is going to be the integral of my velocity function. And the integral of this will be at plus v sub 0 dt. And I get t again is my variable. A is just a constant. I add 1 to the power of t, divide by that. I'm going to get a 1/2 at squared. I multiply this now by t, so I have v sub 0 t plus some type of constant. So this is my general expression, but again, if I have initial information, so if s of 0 is equal to, say, s sub 0, this is my initial position, what I now get is the following function. S of t is going to be 1/2 at squared plus v sub 0 t plus s sub 0. So this formula, again, if you've taken physics before, you have seen this formula. This has always been given to you because you did not have the calculus abilities to derive this yourself. But now that you know how to integrate, especially when you have a constant acceleration, you get this. So if we look at the metric system, that's where usually A would be negative 9.81 meters per second squared. We could plug in negative 9.81 meters per second squared in here, and then we plug in our initial information of position and velocity, and then this would give us our position function. And normally, we're looking at this in terms of projectile motion. We're seeing this as if something goes up and then it goes down, right? So it's going to be some type of parabolic shape that's always formed here, as we expect to be the case with this t squared.